Welcome to the deep dive. Today, we're tackling a really central challenge in AI right now, accountability.
Yeah, it's huge, especially with these incredibly powerful language models that, well, are often kept under wraps by the companies that build them. Closed-weight models.
Exactly. And the big question is, how can we definitively prove that, say, a specific piece of text or maybe some code actually came from Model A and not Model B?
It's a tough nut to crack. We've seen different approaches, right? Things like digital watermarks or looking for statistical patterns, sort of like fingerprints.
But those often have drawbacks, like the provider has to actively choose to put the watermark in, or maybe someone clever figures out a way to generate text that avoids the fingerprint.
They can be fragile. But the sources we looked at for this deep dive, they describe something else, something fundamental.
Yeah, it sounds like a new kind of forensic method. And the key thing is, it doesn't depend on the model creators playing nice or using specific software tricks. It's apparently baked into the AI's architecture itself.
That's the core idea. It's about a geometric constraint, something that applies to the output of pretty much every modern language model.
A constraint that acts like a signature.
Exactly, a forgery-resistant signature. It means the model's output specifically, the log probabilities or log probs.
Those are the scores the model uses internally to pick the next word, right?
Right, those log probs have to follow a very specific shape when you plot them in a high-dimensional space. They're constrained.
And that shape, you mentioned it's an ellipse, or something more complex.
It's technically a hyperellipsoid, so think less like a flat oval and more like a multi-dimensional surface, like an incredibly specific stretched out sphere existing in maybe thousands of dimensions.
Wow, okay, so every single time that specific model generates the next token.
Its log prob vector has to land precisely on the surface of its unique hyperellipsoid. It can't be anywhere else.
That is a powerful concept. Because if you know the exact shape and location of that hyperellipsoid from Model A,
You can check any output. You just see if its log probs fit onto that specific shape. If they do, it almost certainly came from Model A. If not, it didn't.
okay, so our mission today is to really unpack this. Where does this signature even come from? Why is it supposedly so hard to fake? And what could this mean for, actually holding AI systems accountable?
All right, let's start with the geometry.
Mhm.
Because the reason this ellipse exists is actually down to how these models are typically built. It's about the final layers.
And we're talking standard architecture here, stuff you'd find in Llama, GPT, Qwen, those kinds of models.
Pretty much all the big transformer-based ones, yes. There are two key layers right at the end that create this effect.
Okay, what's the first one?
The first is a normalization layer, usually layer norm or RMS norm. You have this internal representation, the hidden state, just before the final decision.
Ah,
Applying normalization to that vector, mathematically, it forces that representation onto the surface of a perfect sphere, a dimensional sphere.
with the keys, the hidden state size.
Yeah,
Often thousands, right?
exactly. Thousands of dimensions, typically.
Yeah.
And critically, this hidden size dollars is usually much, much smaller than the vocabulary size
Wow.
by. The number of possible words the model can output is huge, maybe tens or hundreds of thousands. Correct. So you've got this perfect sphere in the smaller dimensional space. Now, step two. The model needs to project the state into the massive vocabulary space, the math BR space.
What?
So it can assign a score, a logit, to every single possible word it could output next.
Ah, okay, so it's mapping from the smaller hidden space to the giant output space.
Precisely. And it does this using a final linear layer, often called the unembedding matrix. Let's call it dollars.
Okay, a linear projection.
And here's the geometric kicker. When you take a perfect sphere and apply a linear transformation, which is essentially stretching, maybe shrinking, and rotating the space, what shape do you
You
get?
get an ellipsoid.
Yeah.
Like squashing or stretching the sphere.
Exactly. So the very structure of these final layers inherently forces the output logits to lie on the surface of an ellipsoid, a hyperellipsoid, in that final huge vocabulary space. It's just a consequence of the math.
It's not something added on, it's just there.
It's just there. And the specific shape, size, and orientation of that hyperellipsoid are determined entirely by the parameters of those last layers, the unembedding matrix dollars, and the normalization parameters, gamma and beta.
And since those parameters are unique for every single trained model.
The resulting ellipse acts as a unique identifier, a geometric fingerprint for that model.
What I find really interesting here is the self-contained aspect you mentioned earlier. You don't need the whole giant model to check this.
No, that's absolutely key, especially if you're thinking about, say, a trusted third party doing verification. They don't need the original prompt that generated the text.
Or the rest of the model's weights, the billions of parameters.
None of that. All they need are the parameters that define that specific final ellipse,
Yeah.
which is a tiny, tiny fraction of the whole model.
So you can potentially verify authenticity without forcing the company to reveal its crown jewels, the entire trained model.
Exactly. It separates the verification mechanism from the bulk of the proprietary model. That's a huge advantage for practical accountability.
Okay, that sets things up nicely. This sounds quite different from earlier methods. Let's talk about the specific properties the sources highlight. They mentioned 4 unique things.
Yeah, 4 key properties that make this ellipse signature stand out. The first one we've basically covered. It's naturally occurring.
Meaning it just happens because of the standard architecture. No need for the developers to deliberately implement it.
Right. Unlike, say, some watermarking techniques where you have to tweak the model's sampling process to embed the mark, here the signature is an automatic side effect.
Okay, what's number 2?
Number 2 is that it's compact and redundant. This is really efficient,
Meaning?
meaning the signature is fully present in any single output step. Just one logprop vector from one generated token is enough, in theory, to check against the ellipse.
Wow, okay. That contrasts sharply with older fingerprinting methods, right?
Right.
Where you often needed like hundreds or thousands of tokens to build up enough statistical evidence.
Exactly. Those rely on averages or distributions over long sequences. This is potentially instantaneous. Check one token, get your answer.
Very efficient. Then the third property,
Self-contained. We touched on this. Verification only needs the ellipse parameters, not the full model or the input context.
crucial for third-party verification.
Yeah.
And the fourth one, you said this was maybe the most important.
Yes, forgery-resistant. This is where it gets really interesting from a security perspective.
Okay, explain that. We've seen other signatures before, like maybe based on linear constraints. Why is this ellipse harder to fake?
While linear constraints, if you can figure them out, are relatively easy to satisfy, you just solve a linear equation.
Yeah.
But defining and then replicating this high-dimensional ellipse without the original parameters is much harder.
How much harder? Is there evidence for this?
Yes, the research shows this empirically. They tested outputs from known open-weight models like Olmo 2, Llama 3.1, Quinn 3. They checked the output of, say, Llama 3.1 against its own ellipse and against the ellipses of the other models. The distance from the output to its own model's ellipse was consistently tiny, orders of magnitude smaller than the distance to any other model's ellipse. It's a very tight, unique fit.
So definitely unique. But the challenge isn't just uniqueness, it's preventing someone from stealing that unique signature, right?
Precisely. Verifying is easy if you have the ellipse parameters. Stealing those parameters from a closed model accessed only via an API, that's the hard part.
Okay, let's get into that stealing problem. Let's say I'm an attacker, maybe well-funded, I have API access to GPT-4 or something similar. Why can't I just query it millions of times, get the log props for each query, and then use all that data to mathematically figure out the exact shape of its hidden ellipse? Reverse engineer it.
This is where the trapdoor function idea comes in. The researchers use that term. It's like a mathematical trapdoor. Easy to go one way, verify, incredibly hard to go the other way. Steal the parameters.
Why? What makes it so hard?
2 massive barriers. Cost and time. Let's talk cost first, the financial barrier.
Okay.
To mathematically define a quadratic surface, like this hyperellipsoid in dimensions, you need a certain number of data points, a certain number of output samples from the model.
How many?
The number of samples you need, the query complexity, scales with the square of the hidden dimension. It's roughly OD2.
Okay, Guller's is 1,000, so squared is millions. You need millions of sample outputs.
Millions of dependent samples, yes. And getting those millions of samples via API calls costs money. The total cost actually scales super cubically with dollar. It's more like OD3 log d logly.
Super cubically. What does that mean in dollar terms?
The paper estimated this. For a model like GPT 3.5 Turbo, they estimated the hidden size dollars is around 4,650. To get enough samples to define its ellipse via API calls,
Yeah.
over $150,000.
Wow, just in API fees.
Just in API fees. And that's for a model like 3.5 Turbo. Now, scale that up to a big 70 billion parameter model. The hidden size dollar might be more like 8,000 or 9,000.
So roughly doubles, but the cost is cubic.
Exactly. That estimated cost explodes. For a 70B model with approx 811922, the estimate was over $16 million.
$16 million. Just to get the raw data needed to start figuring out the ellipse shape.
Correct. That financial barrier alone basically puts forgery out of reach for almost anyone except maybe nation states. It's prohibitively expensive.
Okay, that's staggering. But let's imagine I have $16 million. Maybe I robbed a crypto exchange. I pay the API fees. I get my millions of data points. Now what? Is it easy then?
Ah, no. That's just barrier one. Now you hit barrier two. Computational time.
What do you mean?
You have this massive data set of points that lie on or very near this unknown hyperellipsoid. Now you have to actually calculate the parameters of that ellipse from the data. You have to fit the surface.
And that calculation is hard.
Extremely hard. The time complexity for the best-known algorithms to do this fitting scales as all of D6. That's dollar to the power of 6. Sextic time.
Sexting time. Dollars to the sixth power. That sounds bad.
What does that translate to in, like, actual time on a powerful computer?
It means the computation time blows up incredibly fast as Galea increases. Remember our 7dB model with $approx. $8,000?
Yeah.
Extrapolating from current algorithms, even if you threw significant computing power at it, the paper mentioned using, say, 64 modern CPUs running flat out.
Okay.
Figuring out the ellipse parameters from the data would take thousands of years.
Thousands of years of computation.
After spending the $16 million.
That's the estimate. So it's not just financially impractical, it's computationally intractable for any relevant timescale. It's secure because it's just too hard and too slow to break.
That combination of cost and time really does make it seem like a trapdoor. Easy to check, virtually impossible to steal or forge for these big closed models.
That's the argument. And it relies on the inherent mathematical complexity, not just some clever software trick that might be bypassed later.
Okay, so this naturally leads to the idea of using this for real accountability. How would that work? You mentioned an MAC system analogy.
Right, like a cryptographic message authentication code. In that analogy, the model provider has a secret key.
And in this case, the secret key is?
The parameters defining their model's unique model ellipse. That's the secret.
Okay. And when the model generates text?
The logprob outputs it produces act as both the message, the content itself, and the tag. The tag part is encoded simply by the fact that the logprobs lie on that specific secret ellipse.
So only someone who knows the secret ellipse parameters, the key, can verify that the tag is correct, that the logprobs actually fit the shape.
Exactly. So imagine a scenario where, maybe due to regulation, model providers have to register their ellipse parameters, the key, with a trusted, independent third party.
Like an auditor or a regulatory agency.
Right. Now, if some harmful or disputed text appears online, that third party can get the log probs for that text.
Assuming they can be obtained somehow. We'll get back to that.
Assuming they can, yes. The third party can then check those log probs against the registered ellipse parameters for, say, model provider X.
If they match perfectly.
Then the third party can say with very high confidence, yes, this output originated from model X. Even if the provider denies it, it provides a strong link for accountability.
And it does this without requiring the provider to open source their entire multi-billion parameter model, which they're obviously reluctant to do.
It's a potentially clean forensic mechanism. But as you hinted, there are some important catches. The sources do point out limitations.
What are the main ones?
Well, two big ones stand out. First, the security guarantee, while practically very strong due to cost and time, is technically polynomial. It's not absolute cryptographic security.
Meaning there's a theoretical, mathematical possibility, however remote, that a much faster algorithm for ellipse fitting could be discovered someday.
It's not ruled out mathematically, unlike some cryptographic proofs. So it's incredibly strong in practice now, but not proven impossible forever.
Okay, that's nuance. What's the second limitation? This seems more immediately practical.
It's all about access to the log probs. The entire verification system depends on being able to get the log probability vector for the output text you want to check.
And the big commercial AI labs, OpenAI, Anthropic, Google, they don't always make getting log probs easy or cheap through their standard APIs, do they?
Historically, no. Access is often limited, sometimes requires special endpoints, or might not be available for all models or users. It's not a universally guaranteed feature.
So we have this really elegant, mathematically robust verification method.
Yeah.
But whether anyone can actually use it for external verification depends entirely on the API access policies set by the model providers themselves.
Exactly. The bottleneck isn't the math, it's the business decision about API transparency.
Which really brings us to the crux of it, and our final thought for today. We've seen this fascinating discovery. The very geometry of how large language models are built leaves behind this unique, incredibly hard-to-steal signature, the hyperellipsoid, in every single thing they output.
It really does seem like a potential game changer for AI forensics and accountability, moving beyond methods that are easier to circumvent or require provider cooperation.
This mechanism offers a path, a way to potentially verify the origin of AI-generated content without forcing companies to give away their core intellectual property, the full model weights.
A path towards accountability, yeah. But it all hinges on one critical thing.
Access. Will the major model providers willingly provide consistent, reliable access to the log probes through their APIs, specifically for external verification purposes?
If they register their ellipse parameters, the key, but keep the log probes, the message tag locked away behind restrictive APIs,
Then the verification system exists in theory, but can't be widely used in practice. They maintain control and perhaps plausible deniability. It really poses the question, who gets to control the narrative of AI accountability when the unforgeable proof is locked behind a corporate access gate?